So first of all, thanks to all of you for being here to this Forum Numerica seminars. It's a bit of a special seminar because it's in between Forum Numerica and also part of the monthly Wimmics seminar. So it's really an honor for me to introduce you Smaranda MURESAN. She's currently visiting the team till the end of June with an invited researcher grant of the 3AI Côte d'Azur. So Smaranda is currently a research scientist at the Data Science Institute at Columbia University, and she's also Amazon Scholar. So before Columbia, she co-founded the Laboratory for the Study of Applied Language Technology and Society at Rutgers University. And while she was there, she was also the recipient of the Distinguished Achievement in the Research Awards. So her research is in NLP, and this is why she's in the team. And in particular on human-centric NLP for social goods and responsible computing. That is also actually the topic of her talk. So thanks again, Smaranda, for being here, and the floor is yours.
Thank you so much for inviting me, and I'm really happy not only to give the talk, but also to spend a month here working with the group of Elena and Serena. It's really, really exciting. So I want to give kind of an overview of the work that we are doing, and then some specific projects that I would like to highlight in natural language processing. So let me start first with with large language models, and everybody knows now about large language model and generative AI, and that's the good part, right? So they have been basically really a cornerstone now in natural language processing, especially developing really applications for social good. And you can see here an excerpt from the New York Times: 35 ways real people are using AI right now. And on the right, copy editor for people with dyslexia, or writing assistance for speakers of English as a second language, and so on. And, we have large language models, and sometimes they are good at reasoning and doing reasoning. And this is an excerpt from Yeji's Choice keynote talk at ACL last year, saying that, if you prompt the model, saying, if you travel west far enough from the West Coast, you will reach the East Coast. So that's a question, and you want the model to answer, and they say the world is round, so you will reach the East Coast, therefore the answer is true. Right, so we say, well, language model can reason. Well, maybe not really, and not always. They are also really not good at reasoning. So that's the bad of the language model. So they're really not good at doing reasoning. And this is an example. The trophy didn't fit in the suitcase because it was too small. What was too small? And then you see the answer of the language model saying the trophy didn't fit in the suitcase because the trophy is the object that is too small to fit in the suitcase, and so on. So it's basically doing an error in reasoning about size and fitting in this case. And if you're really interested about understanding how language models and reasoning works, Ernest David, who is actually a faculty at NYU in knowledge representation, compiled a huge list of all the bad of the language models in this area. There is also, of course, a lot of problem with hallucination. So the example that I gave in the bottom, again, a question answering task, but all the numbers in red are wrong. So these are hallucinated by the models. And then the ugly, of course, language models, they have a lot of bias and stereotype. And I want to give you an anecdote that I recently heard from someone who is working actually in the medical domain. And they task the model, they give a patient record with all the symptoms of the patient and ask the model to generate what was the disease. And the model generated banana pox. So can you figure out what the actual disease was? Think about bias, association, stereotyping. Monkeypox, which is actually a real disease, but it was it just said that maybe monkeypox is bad, but let's do banana pox now. And that, you can imagine the stereotyping, the associations there. Exclusionary norms, toxicity, data leakage is also a big problem, and disinformation as well. So in my lab, I'm working in this like area of using NLP for social good, and we've been working in several areas. Misinformation detection is a big area, NLP for education, NLP for public health, and also NLP and diversity. And I'm going to highlight just briefly kind of an overview, and then I'm focusing on some specific topics guided by the technical innovation in each of these. So in the misinformation detection, we have been looking a lot into this end-to-end fact-checking. So trying to understand, giving a piece of information. So for example, an article on the right, this is an article about climate change, trying to understand, for example, to help journalism, how to fact-check. Like, first of all, what to fact-check? What are the statements in the articles that are check-worthy? Then why to fact-check? Why this will most likely to be false or true? And then how to fact check, right? So basically going and trying to find all relevant documents and retrieving the documents, finding the evidence, and then finally predicting if the claim, for example, is true, false, or mostly true, mostly false, and so on. But one of the biggest challenges here is that, as Brennan was mentioning, it's all this news information is not only simply true or false, there is a lot of misleading content and context. So that's where the fallacy work is, and a lot of fallacy appear in this kind of misinformation work. And one of the projects I'm working here with Elena and Serena's group is working on the fallacy recognitions. In the area of public health, we have been looking a lot again on misinformation, for example, around COVID-19, but we have been looking at other problems, for example, analyzing social media to understand how people move from use to misuse to addiction in the case of the opioid epidemic that is in the United States. And you see an example on the right. So there, what I want to emphasize is that when we are trying to do these predictions of the model, for example, figuring out if someone, one of the stages addiction versus recovery, we don't only want to predict, but we also want to explain why the model, for example, made the prediction. So for example, in this case, generating textual rationales for that. Another project we have on predicting opioid overdose deaths from the investigative reports. So we are working with the New York City medical examiner to look at that. So the idea is that you have these investigative reports that have a very detailed descriptions of the person, of the scene of the death, and we want to extract evidence from this document and make a prediction if it's likely or not. And this, again, it's a prediction of the model plus the explanation that we extract from the text. In the area of NLP for education, we have been looking a lot in improving students' writing skills. So two areas are argumentative writing, so helping students, for example, to identify and recognize or write clear arguments. So identifying argument structure and argument quality, we've been looking in this space. As well as looking at helping students, for example, with creative writing. And then some of the work we have been doing here is, for example, metaphor or idioms or simile generation. So you can see an example, the sky was beautiful, and you want to help the students write, for example, the sky was like a blue canvas. And again, in all of this work, we have been doing collaboration with domain experts, in this case, education and educators. And last but not least, we have been looking a lot in using that NLP for linguistic diversity and cultural diversity. A lot of work has been done in English, so we want to move like just not really on specifically in English or very high resource languages. So we've been looking a lot with theoretical linguists actually in the space of what is called polysynthetic languages, which are low resource, many are endangered, and morphologically very complex. So this is an example that is from Inuktitut, where an entire word that you see there, which I put, it's actually a full sentence. I can't hear very well, it's actually one word. So the task there will be to segment. So if you imagine that if you develop this large language model, it's not gonna work for this type of languages. I'm sorry. And then the other area is cultural diversity. So we've been looking now, trying to see how can we uncover, for example, social cultural norms. So for example, knowing that in Chinese, it's customary to bring gifts to a business meeting for the other party, while in America, it's not necessary to do that. So then what are the challenges across all these areas? And one of the main challenge is the lack of training data. So any type of problems you are trying to think solving, for example, even like, argument reframing or argument understanding, or generating, let's say, metaphors. So we don't have training data to build the system. So that's a big problem. And the other one is the need to model common sense knowledge or other type of domain knowledge, for example. So what are we actually doing across all of these tasks, and the technical aspects that we are working on is how to equip this large language model with knowledge. And we call them knowledge-aware models, where the knowledge can be common sense, or can be domain, or can be cultural norms, or linguistic knowledge. We also really guide all our work on theoretically coming from theories, for example, from linguistics. In the case of the polysynthetic languages, we want, for example, to know information about linguistic typologies and how language similarities. In work on argumentation, we're looking at argumentation theory. We also want to build explainable model, generating textual explanation. And very recently, we are working a lot in the human-AI collaboration space to build high-quality data sets or to help humans to solve tasks. So today I want to zoom in two of the research projects that kind of to emphasize this kind of theoretical and technical innovations that we are looking at. And you can see a lot applying these ideas can go across solving different problems. So the first one is theory-guided and knowledge-aware model. I'm going to specifically talk about an open problem in argument mining, which is called anti-meme reconstruction, and I'm going to define what that is. And then the second one is an approach of human-AI collaboration and as textual explanation. And here, just to build high-quality data sets, and I'm going to emphasize one project on understanding figurative language as explainable textual entailment, and I'm mentioning what that is. And please feel free to ask questions during the presentation. I'm not going to see the one online, but you can ask questions. So the first project is the anti-meme reconstruction, and this is work done with my PhD student and one high school student. And this was very interesting. He was contacting us, and I was mentioning in the previous in the group meeting when I give the talk, I was very surprised. I don't know what you guys were doing when you were high school students. I was not doing research and publishing in conferences. So the task of anti-meme reconstruction, and anti-meme, it's an incomplete argument found in discourse where some components are explicit, but other propositions are left implicit and need to be filled in to really fully understand the argument. And I'm giving here a classical example of Sherlock Holmes' Silver Blaze case. And let me see if I can actually read from here. A dog was kept in the stable, and yet, though someone had been in and fetched out a horse, he had not barked enough to rouse the two lads in the loft. Obviously, the midnight visitor was someone whom the dog knew well. Right, so the task here is to find this missing premise that kind of explain this argument. And the missing premise here is dogs generally bark when a person enters an area unless the dogs know the person well. So our task was given an anti-meme, which is this incomplete argument consisting of a stated conclusion and a stated premise. The task is to generate this implicit and missing premise. And we want to model this task as a text-to-text generation task, and I'm going to mention in the next slides. So there are two key challenges. One is the lack of large-scale data to train the models. We really don't have this example of pairs of conclusion and premises with the missing. We have some smaller scale, which we're going to use for testing. And then the other challenge is the inherent need to model common sense knowledge when you're doing this reasoning task. And again, these are challenges that we're going to come across a lot of problems we are looking in this, but this is an example. So the theoretical insight we used in this work was that incomplete arguments in naturally occurring discourse more often than not require abducting reasoning, which are plausible explanation rather than the more strict form of reasoning based on deductive logic. And this comes from the argumentation theory in the theory of Walton and Reed, for example. Just because I know that not everyone in this room is in NLP and probably know about the large language models, I just want to give like two intuition about the two key concepts and words I'm going to use, which is unsupervised pre-training and supervised fine-tuning. So what is these large language models? In the pre-training phase means that you take this, like for example, a really large collection of data, and you have a task. For example, it's called masked language model. So you mask some of the words, and the task is to predict all these masked words. So you do, and then you train the model. For example, this is just one example. And then in the fine-tuning stage, you have a specific task that you want to solve. So in this case, for example, it's a sentiment classification. Given a movie review, for example, predict if it's positive or negative. So these are the two key concepts that I'm going to mention. So again, our approach for the task of anti-meme reconstruction is a text-to-text generation. So we used a model that was developed, and this work was in 2021. So we use a model called BART, which was a pre-training coder-decoder model. So the idea is that you have an input, a text, and then you generate again a text as an output. So it's a text-to-text generation. In our case, on the left, you see the anti-meme, which is the incomplete argument. So you have vaccination save lives. Vaccination should be mandatory for children. So if you take this text-to-text model and just apply on our task, you're going to generate vaccination save lives, they save money, which is basically just like repeating what the input is with nothing. So it's basically not, they cannot solve the task. So what should we do to be able to solve the task? So we are looking at how to address the two key challenges that we have. So one is the lack of training data. So the idea, we're going to use this insight from theoretical work that abductive reasoning is mostly used in this type of argumentation. So we're going to leverage abductive reasoning as an auxiliary task. And then for the need to model common sense knowledge, we're going to combine this large language model like BART with knowledge models to encode the discourse-aware common sense knowledge. And I'm going to mention in the next slide what I mean by that. So the first task is to leverage this abductive reasoning task. So what we did was in 2020, Bhagavatula et al. Developed a data set called abductive reasoning in narrative text. So what they did was there was in NLP, a very large data set of stories, which is called the ROG stories data set. So what they did, they took the first sentence in a story and the last sentence in the story, and they asked humans to generate the most plausible and implausible hypotheses that explain these two sentences. So basically, what do you mean? Like starting a story and ending, what was missing in between. So they generate this large data set. So just to give you an example, Amy was looking through the mother's old scripts book. Amy realized her mother had dated her history professor, right? And the human generate, Amy found pictures of her history professor and mother together, for example. And this was, this way they build using humans crowdsourcing on Amazon Mechanical Turk. They actually developed this large data set that now has, let's say, 50,000 training instances. So the idea is that can we use this to basically fine-tune our model? So the idea is that we use this data exactly for this task-relevant training, which is the fine-tuning step. So in the input now, which is the input to the encoder of BART, you give this, the two sentences, observation 1, and use a separator, and then observation 2, and then the output to the model is the two sentences and the hypothesis in the format of observation 1 and since hypothesis observation 2, because we wanted to make sure that this is kind of a coherent discourse. And then we train the model. And then in the inference step, you just apply our examples. So in this case, you can see the same example, vaccination save lives, vaccination should be mandatory for children. And now the generation gives us a better implicit premise, which is the one in blue that I'm trying to see, vaccination are the best way to protect children. Right, so fine-tuning on this abductive reasoning task is generating more plausible premises for the task. But the question is, can we do better? And the idea is, of course, in all of this inference, we might need to know about information about common sense knowledge, both in general about word knowledge and the discourse. So we're going to use the ParaComet discourse-aware model. And just before I'm talking about that specific, I'm just going to tell you, like in 2 slides, what knowledge models are, just in case people are not familiar. So what is the key idea, right? So the large language model encodes some sort of knowledge. When you train a very large amount of text, you expect they're going to encode some sort of knowledge. But it's not only, good enough for common sense. So what at the University of Washington, Bostolet et al. Developed this idea where they retrain this large language model on knowledge graphs in order to be able to learn structured knowledge. So the idea is that you take these pre-trained large language models, and then you take the knowledge graphs. And in this case, for example, you can imagine ConceptNet or any type of graphs, and then you take an entity and the relation, and then you generate the other entity. So for example, you have a knowledge graph where you have mango is used for salsa. What you do, you actually take mango used for, and then you generate salsa. So I think you do this kind of pre-train. And then they train, I think, GPT-2 at that point on this large knowledge graph. So you transform knowledge graph in these triples, and then you train it. And the resulting knowledge generalizing structure to other concepts. So that's the main idea behind this, what I call knowledge models. What we did is actually there was an advancement in 2021. Gabriel et al. Enhanced this model with information from discourse. They call it ParaComet, from paragraph knowledge. So this is extension of these knowledge models to the discourse-aware common sense knowledge. So what can these models do better than before? So if you look, for example, in this figure that is taken from Gabriel et al., if you look at sentence 4, like Ella walked around the property, and you want to have the information, for example, what was her intention, which is usually encoded in these knowledge graphs. So, if you imagine that that's only the sentence that you are giving, Ella walked around the property, what was the intention? Maybe, just to want to take a break, she want to, but then if you're looking at the entire discourse and you look at the first sentence, the water bill at Ella's house had been high, right? And now you have the sentence, Ella walked around the property. So now the intention most likely will change because Ella maybe wanted to find a leak or to fix the pipe and so on. So the idea is that these models now not only take information from outside this knowledge graph, but also information from the current discourse. So what we did is actually we really use this idea of trying to use ParaComet for our task. So our discourse is actually formed from these 2 observations from the abductive reasoning in narrative text dataset. And then we use the output of ParaComet, which are these 9 common sense relation, cause and effects, mostly for these 2, observation 1 and observation 2. So, and for our experiments, we just use one particular type of relation, which is a cause relation of the intent of one of the entity to do something. So with this, what we did, we took the input again, which was these 2 observations, but now we also added the common sense information that was derived from this ParaComet. So Amy was looking through her mother's old scrapbooks to find something. Amy realized the mother had dated her history professor, and then the output is the same. So we fine-tune now this part model on this enhanced data set. So now giving at inference time, again, giving the same example, vaccination save lives. Now we run ParaComet to derive common sense information, and then is this the common sense that comes is to stop disease, and vaccination should be mandatory for children. And now the output would be vaccination are the best way to prevent childhood diseases, which is an even more plausible, implicit premise for this task. So this was the main idea that we have. And then we test the model on 3 different data sets of these anti-memes. And these were all annotated by humans. So that we have, the first one was around 1,500 examples from the argument reasoning comprehension task that was run at the semi-eval evaluation in 2018 from Habernal et al. In Irina Gurevich group. Then the data set was much smaller, and this contains these anti-memes from online discussion groups, again with human-generated implicit premises. And then the third one was even smaller, a microtext corpus of argumentative text, again with human-generated premises. So what we wanted to do is to test the model. The first one is the zero-shot case that I showed at the beginning. The other one is when we only fine-tune on this abductive reasoning task, and then when we also add the knowledge. So this ARK will be the one where we look at knowledge. So we did both automatic and human evaluations. So for the automatic evaluation, we look at the BERT score, which is basically a metric for evaluating text generation using contextualized embedding. So basically trying to look at similarity. And here we compare the model-generated premise with the human reference. And then if you look at the column, with the first number score column, you see that the model that uses knowledge is better than the other ones. And in the human evaluation, we only focus on the last two, basically the one that is using the abductive reasoning and the knowledge. And we use 50 examples from each of the test sets, so 150. And we judge on the metric of plausibility. And ask the human which if the model is plausible or not. And the human agreement is a 56 Kipernov alpha, which is a moderate agreement. And we can see that the model using knowledge is more plausible, but we are still far away from really solving the task for this. So the conclusion from this part is really using theoretical insights about the phenomena, in this case, help us to even think about how to approach the problem by using abductive reasoning, for example, and deal with the lack of training data. Combining language model and knowledge model to plan content and add control to generation system, I think this is very important. Thinking about evaluations, and I think a lot of time for text generation models, we should think about human-based evaluation just to make sure that the task is, the output is correct besides the automatic metrics. And in the next steps, what we're looking at is to explore other type of common sense knowledge. We only look at causal, but for example, if an argument make an argument from analogy or from other type of inference rules, you might want to do other type of knowledge to include, and then we are looking at guiding this generation by the argument schemes in the argument. So other problems that can be solved using knowledge-aware model and theoretical insights that we looked at, for example, was figurative language generation. We look a lot at metaphor generation, for example, and we use conceptual metaphor theory for that, irony and similes. We look at argument reframing, making an argument more trustworthy, for example, and then fallacy recognition that guided by the fallacy theories and argumentation. So I can stop here for questions, or I can go to the next one and take question at the end. At the end, okay. So the second part, I want to emphasize another kind of methodological line of work. We are looking now at human-AI collaboration. And particularly initially start to look at building high-quality data sets, because we are lacking for a lot of tasks in NLP high-quality data, both to train the model and to evaluate, and also the textual explanation. So I'm going to go over one example of this on figurative language understanding. This was a paper at EMNLP last year with my one of my PhD students at that point and one undergrad. So understanding figurative language has been framed, including by us before, as which, and then figurative language I understand here sarcasm, metaphors, similes, idioms. And this can be framed as a recognizing textual entailment task, also known, this was introduced as textual entailment in the 1995 by Ido Lagan, and then renamed as natural language inference by researchers at Stanford. And I kind of it's stuck with the natural language inference afterwards, but these two are very, very similar tasks. So the idea here, for example, if you look at if you try to understand a simile, for example, the place looked like a fortress, right? What it means is that the place looked impenetrable and inescapable. So this is a task of entailment. So the entailment means that giving two pieces of text, you want to mention that one text entails the other. Or contradiction, which is, for example, in the sarcasm, I love going to the dentist, which actually the actual meaning is I hate going to the dentist, right? When you are ironic or sarcastic, you are mentioning the opposite of what you want to say. So that's exactly the type, the notion and the task of textual entailment, trying to give two pieces of text, does one entail, contradict, or there is no relation between them. So we can try to frame the language understanding at this type of textual entailment task. So what are the issues if we are trying to do that? And all the current, at that point, data sets had an issue which is common actually in NLP, in the natural language inference and textual entailment data sets. They are suffering from spurious correlation. So what I mean by that is that researchers have shown, for example, you have two pieces of text. One is called hypothesis, the other one the premise. Just giving the hypothesis to the task, it could actually predict correctly if it's an entail or contradict without even having the other pair. So there is something in the data or in the way that it looks like, it's really, it's basically the model doesn't learn to solve the task. It's just the data set has annotation anomalies. Sometimes the label is associated with the overall sentence, not the meaning of the figurative language. So we wanted to really focus on understanding the expression. And then not all the data sets have both entailment and contradiction for the same type. So what we wanted to do is to not only to make this task as an entailment, but also to provide an explanation for the prediction of the model. Because then the idea is that then we understand better if the task is actually solved, if the explanation is correct, for example. We focus on the 4 types of figurative: sarcasm, simile, metaphor, and idioms. The entailment and the contradiction labels are related with the meaning of the expression. And we also want to make it more varied rewriting of the hypothesis and the premise to minimize trivial prediction. So the example that I give to love the dentist or hate, the model can quickly learn just because there is these antonyms and everything else is the same, right? So it might be a very simple problem. So here is what we want to do is basically we would want to create a data set that looks like this, kind of to solve the task. So you have, I have not had any sleep for the past 3 days, only to come back home and my neighbors are having a loud party. And then you have, I'm really thankful that my neighbor is having a loud party when I'm not had any sleep for the past 3 days. Right, so that's an example of a contradiction. This is an example of a sarcasm, the hypothesis. And the explanation would be a neighbor having a loud party can be destructive and keep someone from getting much needed sleep. So being thankful about it is unrealistic. So that's kind of an explanation. So that's what we want to generate in our data. And this will explain, for example, the implicit meaning. It requires multiple reasonings, like, for example, loud party is disruptive, disruption is the lack of sleep, and lack of sleep is angry and upset. So we created this data set using what we call then a model in the loop approach. So we use this large language model at that point, GPT-3, and we create this data set of 9,000 pairs. And we implemented the baseline model then to solve the task as an explainable entailment. And we introduce a new evaluation metric to combine label accuracy with explanation quality and then do evaluation, both human and automatic. So let me give you just the intuition. I'm going to choose one of the figurative language just so that otherwise it's going to be too long. So I'm just going to give you how we use that to generate, for example, for irony and sarcasm, this data set. So the question was where to start. Right, so we thought initially to start, well, we can take sarcastic message and we want to generate the literal. However, how we select the sarcastic messages, a lot of research before has been using at Twitter using hashtags, but they are very formulaic if you're doing that way. So we decided we go the other way. we started with literal sentences. And for this, we use a dataset that was released by Meta, I think, on empathetic dialogues, which are literal sentences annotated with negative emotion. And the reason we started with that was that a lot of time in irony, you say positive sentiments towards a negative situation, right? So the negative situation should be the literal meaning. So we started with that. And then we tried to figure out how to use the model in the loop, where the humans, kind of the question was, what are the humans good at and what are the machines good at? So we use in our previous work, we showed that it was a different task. We asked the humans to, for example, giving a sarcastic message, rephrase what is the implicit meaning. And they were doing just these minimal edits. Like, I love going to the dentist, I hate. So they were really doing very minimal edits. So they are not good, the humans are not good at doing large edits to create diverse entailment pairs, but they are good at doing minimal edits and making sure the sentence is entailed or contradicting. So they do the logical between the two sentences, but they don't do well of like rephrasing a lot. But the models like ChatGPT-3 is not good at generating sarcasm, at least it was not then. I'm not sure how the new models are. They are still not there, but they are great at paraphrasing, right? So we try to take advantage of these two things. So let me show you how we use this model in the loop. So we started first on the yellow things we see there. We started with the empathetic dialogue data set. So you stay with a literal sentence, like for example, in the bottom you see an example: my next door neighbor are always arguing in your shared hallway, and the emotion. And we prompted GPT-3 to basically giving this literal and the emotion, please paraphrase, paraphrase, we give an instruction with few short example to paraphrase this literal sentence. So the model generates, it's so annoying to have to hear my next door neighbors argue in the hallways, our shared hallways. So now that we have that, what we did is actually we have an expert verification step after that, just to make sure that the generated paraphrase is correct. And then if it was not, it was the model, we resampled from the model. And then once we have that, we ask the mechanical Turk to then giving this literal sense now, that paraphrase from GPT-3, which is the green example, we asked to rewrite this to be sarcastic. So as expected, they were just doing these minimal edits, like it's so annoying to have to hear, and they realize it's so pleasant to have to hear my neighbors. However, now if we pair the example in red with the original one, we do have a much better paraphrasing and different, not really like a minimum edit. So it's a much better entailment pairs. So then we do an expert verification step, and then the data creates the literal and the sarcastic are the contradiction example, and then the literal and the paraphrase, which is in green, are the entailment. So this is the way we create this type of data set, both with entailment and contradiction pairs. Then we do, again, for explanation generation, we give them the pair of the hypothesis and the premise and ask the model to generate an explanation, for example, why a pair is an entailment or a contradiction using GPT-3. We give 13 examples, and then we have an expert validation and correction step for that. And then you can see here the proportion of time that we had to, the human expert has to modify slightly the editing of the explanations. So this is the data set that we created and the numbers of examples that we have. And let me say, this is an example of a prompt, for example, for contradiction. You'll be presented with example of, like for the contradiction on the right and sarcastic sentences, your task is to rewrite the explanation and so on. So you give this literal, when I moved to my apartment, it was full of bugs. I absolutely loved when I moved to my apartment and found calling with certified of them, therefore it is unlikely to love seeing someone's apartment infested by them, right? So that's the explanation. And these are some examples. So the figurative language is in the hypothesis column. So this is the example on the sarcasm, but you can look also, we generated for simile, metaphors, and idioms. So if we look at the example of a simile, for example, in fact, the assembly hall was now like a steam sauna. And then the contradiction premise, which is on the left, if I can read, the assembly hall was now cold and dry, more so than usual. And then the explanation, which is on the right column, says a steam sauna is a small room or hut where people go to sweat in the steam. So it could it would be hot and humid, not cold and dry, right? So the explanation kind of explain why it's in a contradictory example in a more detailed way. So for this, we did an experimental setup to basically a baseline model. We did what is called a self-rationalizing model, which the idea is that you give an input to the model and you are supposed to predict the output, which in our case is the label, entail, and contradict, as well as the textual explanation. And for this, we use these text-to-text transformer models, T5. And we give it, all the examples are giving an instruction. So for example, does the sentence premise, entails, or contradicts the sentence hypothesis? Please answer between entail and contradict and explain your decision in a sentence. So for people who are not familiar with the T5 models, I'm just going to give it one slide and the idea. So this was a very important model developed in NLP. And basically what they did, they transform all the natural language tasks in this text-to-text framework. So you can imagine a translation task is, you can see it in green, translate English to German, that is good. And then das is good, I don't know, people who know German. So basically the output is on the right. But then this is normal, like a translation, you can see it as a generation task, but they did this everything on all the tasks. So for example, the cola, it means to judge acceptability of the sentence from a grammatical point of view. So you have cola sentence, the course is jumping well, and this is basically the generation is not acceptable, which is the label. So they generate all the NLP tasks and all the data sets in this text-to-text model, and then you train a multitask model for text-to-text model for that. So this was a very big advance, and I think a lot of research now, like kind of using these models. So for us, what we did was we used this model once on our data set, but then we also fine-tuned it on a very, very large, I think it was like 50 times larger than our data set, which was an explainable entailment task that was generated before. And we wanted to see if our data is much better in terms of the explanation that we generate. So we did an evaluation, both automatic and human. So for the automatic evaluation, we did not only the accuracy or the F1 measure at on its own, but also at explanation score quality, where we look at explanation score as being the average between BERT score and BERT. So these are two metrics to evaluate the quality of text generation. So we can imagine, for example, accuracy at 0, at 50, and 60, and so on. For the human evaluation, we did given two sentences that does the explanation justify the answer above, and we ask human to rate it as yes, weak no, and no, and we computed a score, which is a sample average of the explanation score across the three Turkers. So these are the results, and I want you to look at the right, that the T-flute is our data. So it's particularly if you look at the accuracy at a higher quality of explanation score, like 50 and 60, comparing with the T5, which was just fine-tuned on a general explanation, explanatory textual entailment data set, we do much, much better. And also the quality of based on the human evaluation is much better. And these are some results of looking at the quality of the explanations, comparing using our model rather than using models fine-tuned on existing data sets. And we see that we have better in terms of these metrics as well. And this is an example where you have the camp life really had energized him, the life in the camp wilted him. And this is the contradiction. And the gold explanation is to wilt means to lose vitality or strength, while the energize means to give strength or energy to. If the model trained on the ESNLI data, which is another explanation entailment model, it's really bad. Like, so if the camp life energizes him, then he is not wilted, but it doesn't really provide an explanation why. So our explanation is much better, again, providing the definition. To wield something means to lose energy and so on. And we run this in the shared task. We use this data set for a shared task on figurative language understanding at the MLP last year. We had 5 teams participated and several beat our baseline, again, using more knowledge-aware model, and we were very happy about that. You know, if you're interested, please look at our report. But one interesting fact that we found from one of the papers, we were trying to look exactly to find if our data set have these spurious correlations about if you run just on a hypothesis on the premise, are you doing the same good results? And you can see that the first line, which is regular, means that we use both the hypothesis and the premise, and they achieve good results, 92, for example, accuracy at 50, 87, and so on. But if you use only hypothesis or only premise, the results go really down. So this was actually a very nice result showing that our data does not have this issue of spurious correlations. So the conclusion is that the human collaboration framework for building high-quality data sets, I think this is a very promising direction. Providing textual explanation for model prediction, I think it's important. And I think we should think about building these metrics to account not only for the quality of the explanation, but only for model prediction, but also quality of explanation. And we did something very, very basic, but I think there is a lot of space to improve here. So other tasks that can benefit from this idea of human-AI collaboration and explanation. So we've been working on cross-cultural norms, similarity and differences, and explainable models again, and we are planning to have this submitted to MLP. We look at generating visual metaphors from linguistic metaphors, and this is a paper in Findings of ACL. And the idea here is to collaborate between large language model and diffusion-based text-to-text model and human. So this is a very nice result. And then last but not least, classifying and explaining fallacious argument. And this is something I'm excited to work with Elena and Serena's group here. I think kind of the concluding slide. I really think there is a space for large language model to do a lot of work on social good and responsible computing, but for this we need smaller, and I would argue for this neurosymbolic model that learn from data and knowledge, including knowledge about common sense, domain, linguistic, sociocultural norms. I would argue also that they can be joined like really explainable models as well. Using theory guiding models and trying to use theoretical insights from the domain that you are working on, looking at evaluation and metrics, and then the human-AI collaboration for data sets, task, and ultimately, I think also aligning better with human values. And this is not a work that we can do only as, I would say, NLP researcher. I think it's a lot of work on interdisciplinarity, community policymaker, and cross-sector. And the last words is, I work a lot on figurative language. And this is a quote I like from Kundera: "Metaphors are not to be trifled with. A single metaphor can give birth to love." And my rephrasing it, because I work on generation, is theoretical insights, knowledge-aware, and interactive models, high-quality data sets, evaluation methods, and metrics are not to be trifled with. They can give birth to love for explainable natural language understanding and generation for social good and responsible computing. And thank you for my PhD students and postdocs, undergrads, master students, and my collaborators. Questions? Visual metaphors.
Thanks a lot, Smaranda, for this super interesting talk. So are there any questions?